Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the chi-square distribution. And why am I talking about this is because it is related to understanding or studying the sampling distribution of the sample variance. So sample variance here is S squared, okay? Now we're going to start off with understanding the relationship between a gamma distribution and a chi-square distribution. Well, if you have a gamma distribution, therefore the probability density function is given by this equation or this function right here. And this is supported for x greater than 0. So this is something that you have seen in the continuous probability distribution, examples of continuous probability distributions, yes? So if you let alpha equals v over 2, where v is the parameter that represents the number of degrees of freedom, and if you let beta equals to 2, therefore the gamma probability density will then be transformed to what looks like this. So beta here is replaced with 2 and alpha here is replaced with v over 2. This is known as the chi-square probability density. Therefore here is our x here. X is our random variable and x has a chi-square distribution. So x is a chi-square random variable and it can be described by this probability density function. So if I want to ask probability questions related to x, for example, if I want to ask what's the probability that my random variable x here is greater than a, by right, what I have to do is I have to integrate this big function here. So we have this function that looks like this. So I'm just going to write down this one here too. So it looks tedious really. So blah blah blah. So you're going to write down this whole function here. You're going to integrate that with respect to x. And the limit here is going to be greater than a, which means a is the lower limit. And you will integrate that, the upper limit here is going to be infinity. So that's the process that you have to do if you want to find the probability related to our chi-square random variable. But we don't have to do that because we already have a chi-square distribution table. So this is the table that has already done certain calculations related to this integral given here. Okay, so this table here, for example, this table here gives the area. This is the area. That means this is the probability really. So what it does is it integrate the function that you see here. So this function, so I'm just going to write down fx dx from a value. So here is the lower limit, which is x2. So here is the lower limit until infinity because you go on in this direction. So the upper limit here is infinity. Basically, it's asking the probability of x greater than or equal to x2, yeah? So that's the process. Therefore, if let's say you have x is a chi-square distribution with degrees of freedom 7. Okay, so I'm just randomly picking some degrees of freedom. Let's say 7. I'm just going to explain what is the meaning of this value 1.69. So it means that you are doing the process here where probability x greater than 1.69. Okay, probability x greater than, or it could be probability x greater than or equal to, doesn't matter. So probability x greater than 1.69 is going to be the process that we do here is you're going to integrate from 1.69 until infinity of that probability density function given here. Okay, and the result that you get is 0.975. So that is the area, 0.975. So that is the process. By right, you have to do it on your own, but we don't have to because we already have the table that gives you the result. Okay, and if you want to visualize how does it looks like, well, it is like this. So the starting point here is 0. It gets bigger, larger value towards the right side of the distribution, and because the area is quite big, 0.975, so we know 1.69 might be somewhere here, and this is the area, which is 0.975. So if I ask you what's the probability of x less than or equal to 1.69, and that means I'm looking to find this area less than, and that can be easily obtained if you consider total area. Total area is 1, and you will minus this area, so 1 minus 0.975, so the answer is going to be 0.0225. So that is a little bit of idea on how you can use the chi-square distribution table to answer probability questions related to a chi-square random variable. So we don't have to do this integral process here. Okay, right, let's move on to the next relationship, which I think is a bit important here. We have a relationship between the standard normal distribution with a chi-square distribution, and the relationship is given as such. Well, if x has the standard normal distribution, what it means, standard normal distribution means x has a standard normal, not just normal, but standard normal. The mean has to be 0, and the variance is going to be 1. Okay, so that is the definition of standard normal distribution. Therefore, if you take this random variable and you square it, so if you take x and you square it, so the standard normal here, the standard normal distribution random variable, the standard normal random variable, and you square it, the result here is going to have a chi-square distribution. Chi-square distribution with degrees of freedom 1. So chi-square distribution can be represented as chi-square. This is the degrees of freedom, and here it will have chi-square with degrees of freedom 1. Okay. If you want, you can call, or you can think about it as a new random variable. We can call it y. So x here is originally a standard normal random variable. So if you square the value of it, you can call it y for simplicity. And so y has a chi-square distribution with degrees of freedom 1. Okay, so instead of x squared, y has a chi-square distribution with degrees of freedom 1. Okay, now let's try to imagine the process if we have several independent standard normal random variable. Okay, so let's say that I have this one here. So let's say I have x1, x2, xn. Each has standard normal distribution. Okay, so each of them has standard normal distribution. Therefore, if I take all these values, if I consider all these values and I square it, okay, so this is standard normal and I square it, And because they are independent, okay, let me just write down, each is also independent. Okay, independent. So therefore, if you consider this process here, I'm just going to call all this thing as y. So y represents the process where you take all this standard normal random variable and you square it. Well, therefore, you can see that if standard normal random variable you square it, the result given here is going to have a chi-square distribution with 1 degrees of freedom. This is also a chi-square distribution with 1 degrees of freedom. This is also a chi-square distribution with 1 degrees of freedom. Based on this simple result, first we can extend to this process given here. So therefore, what I can say is, therefore y, where y here represents x1 squared plus x2 squared and so on, therefore y is going to have a chi-square distribution with n degrees of freedom. Okay, the degrees of freedom is going to be equal to n because here we have 1 degrees of freedom, over here is another 1 degrees of freedom, this one here is another 1 degrees of freedom. So the total degrees of freedom is going to be equal to n because we have n random variables. Okay. Now this result here can be easily extended if you have, for example here, independent chi-square random variables. Okay, so this is another result. So here what we have is we have x1, x2, xn. They are already a chi-square random variable. They are not standard normal, they are already a chi-square random variable. Therefore, each of them has its own degrees of freedom. For example, x1 here might have some degrees of freedom. X2 here might has its own degrees of freedom. It can be similar to V1. It can be totally different value. Xn will have its own degrees of freedom. So they all have different degrees of freedom. They are all independent. Therefore, if you consider this process is the process of adding up all these independent random variables, which means you have x1 plus x2 plus blah 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 xn. So we're just going for simplicity, we call it y. So this is equal to y. Therefore, y here is going to be a chi-square distribution as well, because everybody here is a chi-square, has a chi-square distribution, right? So each of it, they are all have a chi-square distribution. Therefore, it makes sense that y must have been or should have been a chi-square distribution as well. So y is going to be a chi-square distribution where the degrees of freedom is going to be the values of all degrees of freedom added up. So we're going to add up degrees of freedom for the first random variable plus degrees of freedom for the second one, and you're just going to add up all the degrees of freedom. So that's the idea. Okay. Right, now let's move on to the next slide. So the chi-square distribution is useful in making inferences about sample variances, which is S squared, and recall that sample variance is a statistic. And again, this chapter is about understanding the distribution of statistic. Therefore, here are the following important results related to the distribution of statistic. Okay, so here, if x bar and s squared are the mean and variance of a random sample of size n from a normal population with mean mu and standard deviation sigma. So here it means, or it implies, that our original distribution, which is x here, the original random variable x, has a normal distribution with mean mu sigma squared. Okay, and then you get sample from this, and you get x bar and you get s squared. So in this situation, x bar and s squared are independent. And then if you consider this random variable, why is it random variable? Because it has s squared in it. S squared is a statistic, it is also a random variable, so the result here is going to be another random variable, another statistic. Therefore, this whole thing here, you can call it y if you think that it makes things simplified for you. So the whole thing here, or you can say that y, which is equal to n minus 1 s squared over sigma squared, will also has a chi-square distribution with degrees of freedom n minus 1. So this is the result related to the distribution of, some part of the sample variances s squared here. Not exactly the distribution of s squared, but this is the quantity that has the statistic s squared in it, okay? Right. Now, let's try and play around with this mathematical process right here. Well, it says here if x1, x2, xn come from a normal population with mean mu and variance sigma squared, so you need to verify that this following statement is true. Okay, so what I'm going to do is I'm going to start off with the left-hand side. So here what I have is left-hand side is xi minus mu square it. I'm going to do some process so that at the end of it I will get this result here. So okay, that's what I'm going to do. Now notice that we have some term here related to x bar and x bar. So what I'm going to do is I'm going to start off with having xi minus x bar plus x bar minus mu, and you square it. So notice that I have introduced something which is negative x bar plus x bar into the original part here. But notice that this is the same thing as introducing 0, because x bar and negative x bar will actually cancel out. So it means that I introduce something without changing the original statement that I have here, and that is what we call manipulation, right? So we are going to manipulate using these terms here. We are going to use these terms to make the process of proving a bit easier. You will see later on why I said so, okay? So here I have introduced the terms here, but this is okay because it doesn't change the original expression that we have here, okay? All right. So now what I'm going to do is I'm going to group these two together. Okay, I can do this, I can group these two together. And if you want, you can think about it as this is like A, this is like B. So it's like having A plus B and you square it. And the result is going to be A squared plus 2AB plus B squared, right? So this is what I'm going to do. And you will see why I do this, because then, like I said, it will make the process much easier. So what happens if I consider that? Now let's move on. Okay, so if I expand this thing, so you can think about it as A and B, like I said just now, A squared, so that means xi minus x bar, and you square it. I hope you can see that now I've got this same look as what I'm supposed to prove, right? So here I've got xi minus x bar squared. Next, I will have 2ab. 2ab means 2 times xi minus x bar minus mu, 2ab plus b squared, which is x bar minus mu, and you square it. Okay. Now I can separate all this process here into three different parts. Okay, so what we have here is, next I can write down in terms of this. xi minus x bar square it plus 2 is a constant. You can take it out from the summation process. So n I equals to 1 xi minus x bar minus mu plus okay, so that's it. Next, what I'm going to do is well, this part here has already looking similar to this part. Okay. I'm just going to explain part by part because I don't have space. Okay, next I'm going to explain what happened to this one here, to this one. Okay, so sorry for that. Okay, so what we're going to do next is I'm going to explain this part. Hang on. So this one here. Okay, this one. Okay, right. So for that one, we can see that it can be further simplified as 2. Okay, we can expand this part. So we have xi times with x bar. And then we have minus xi with mu minus x bar you square it plus x bar mu. Okay, so that's what happened. Next, it becomes 2, and then you can consider the process separately. Xi x bar minus mu is a constant, actually you can take it out, xi. Okay, so this one is minus x bar squared plus x bar mu. Okay, now this one here, x bar is a constant, you can take it out. Okay, so but first I'm going to show you what happened to this guy. Summation of xi. Summation of xi is equal to an x bar because we know that x bar is the sum of all the x over n. So this is the formula to get x bar. Therefore, the summation of xi, which is this one, the summation of xi is equal to an x bar. Okay? Right, so I'm just going to write down that part. Okay, so here we have it's equal to 2. X bar is a constant, we can take it out. The summation of xi and I equals to 1 minus mu. Again, this one here I've already explained to you just now. This is equal to n x bar. Now x bar here is a constant, x bar squared is a constant. So if you sum until n, the result here is going to be n x bar squared. For example, if 3 is a constant, and what's the process here? That means you have to add up 3 plus 3 plus 3 plus 3 until n times, which is equal to n times 3. 3 is a constant. So again, x bar squared is a constant. If you have the summation process right next to a constant, the result here is going to be n x bar squared. Similar to this one, x bar mu is a constant. So the result is going to be plus n x bar mu. Okay. Next, I'm going to simplify that further. This one here is going to be x bar times with nx bar. So here is nx bar. So x bar and x bar. This one is minus mu and x bar. This is minus nx bar squared. This is plus this is plus n x bar mu. Okay, therefore you can see that n x bar mu can be cancelled with mu n x bar. Negative n x bar squared is the same thing as this one here is positive n x bar squared, which can be cancelled out as well. So this part here is going to become 0. Okay. Next, let me explain what happens to this one. So again, you can see that x bar minus mu squared is a constant. So if you have a summation process next to a constant, like I told you right here, this is a constant. That means you have to add up the constant n times. That is the process, 3 plus 3 plus 3 until n times. So that means the result is going to be n times 3. So the same thing with this one. The result for this one is going to be n times with x bar minus mu, and you square it, which is what is given here. So we have managed to show the result is as such. Okay. Okay. Next, let's move on to this last slide. Assuming that statement 1 in page 19 is true, this is not actually page 19, and using the result seen in example 8.5, which means this result, we're going to use this result, we're going to prove that the statement number 2 given in page 19 is also true. So this one is actually related to this statement here. We're going to assume this is true, and now we're going to prove that this is true. So we're going to prove the second statement. Okay, just going to prove this part. Okay. All right. So what we're going to, the information that we have, okay, we're going to start off with the information that we have. The first information is we have x1, x2, xn comes from a normal population. Okay, according to this one here, it comes from a normal population with mean mu and standard deviation sigma. So here is the information. They all have xi. Okay, we're going to call this xi. It has normal distribution with mean mu sigma squared. And from here we can get a random sample of certain size. And we have x bar and s squared, where x bar and s squared are independent. Okay, so this is the information that we have. This is the information that we have. Next is we're going to use this result. Okay, so here is the summation of xi minus mu squared is equal to the summation of xi minus x bar, you square it, plus and x bar minus mu, and you square it. So this is the result, xi minus x bar, xi minus mu. Okay, so this is from I equals to 1 and I equals to 1 until n. Okay, now we need to prove that, okay, what we need to do is we need to prove that n minus 1 s squared, this statistic or this random variable, if you want you can call this whole thing as y. So this is y. So we need to prove that y has a chi-square distribution with degrees of freedom n minus 1. Okay. Right, so how are we going to start this off? Well, we're going to start this off with writing down. Okay, so this is the information. Okay, so this is the information, and now we're going to start the process. So here we have, let's say we start off with writing down what is n minus 1 s squared over sigma squared. What is this? So this is actually equals to n minus 1. What is s squared? S squared is, well, I'm just going to write down this one, xi minus x bar, you square it over n minus 1, right? So this is sample variance. Okay, and we are going to use this result here. That means I'm going to use this result, xi minus x bar squared over n minus 1. This is given by this one, and from this equation here, I know that this is equal to this guy minus this guy. Okay, so I'm going to write down what is s squared now. So s squared is n minus 1 s squared. S squared is this thing, which is xi minus x bar, you square it over n minus 1. This one here is over sigma squared, which can be written as times with 1 over sigma squared, right? It is the same thing. Therefore, this part here can be cancelled out with this one. And I'm going to use this result here. So it says you have to use the result in example 8.5. Therefore, this guy here is going to be replaced with this thing minus nx bar minus mu squared. Okay, right, this guy is the same thing as this one, and we're going to substitute that one with xi minus mu squared, this process, minus this one. Okay, so that's what I'm going to do now. So that one is ni equals to 1 xi minus mu, you square it, minus n x bar minus mu squared over, okay, I'm going to bring back sigma squared at the bottom here. Okay, now what else that we can do? Well, okay, so what I can do is I can separate these two process here, so it will be looking like this. We will have n minus 1 s squared over sigma squared is equal to, okay, oops, sorry, is equal to this guy minus this guy with sigma squared at the bottom. Yeah, so we have xi minus mu, you square it over sigma squared, minus n x bar minus mu, you square it over sigma squared. Okay, so what are we going to do next is, well, I hope you can see that this one is from I equals to 1, and I hope you can see that sigma squared is a constant. When it is a constant, you can either consider it to be outside the summation process, or you can also put it back into the summation process, right? Okay, so let me just show you what is this all about. This part here, okay, so I'm going to just focus on this part here. So here we have xi minus mu square it over sigma squared. This is the same thing as having 1 over sigma squared multiply with this process. Okay, and again I say this is a constant. Whenever you have a constant, you can also put it back inside if you want. So you can write it down in terms of, yeah, Okay, and if you have squared here and also squared here, what you can do is you can combine the process. For example, if you have 1 over 4, you square it with 2 squared, you can combine the process by writing it in terms of 2 over 4 and you square it. It is the same thing, because when you expand it, you will get 2 squared over 4 squared. Yes, so that's what we're going to do for this one here. I can write it in terms of xi minus mu over sigma, and I square it. It is the same thing. Okay, so that's the explanation related to this part. Okay, so that's what I'm going to do now. I'm going to write down the result here. So the result here is going to be equal to this one. We can write it down in terms of n I equals to 1 xi minus mu over sigma and square it. Okay, let me go and further explain what's going on. So what is the process all about? So the process here can be written as, well, we have x1 minus mu over sigma, I square it, plus x2 minus mu over sigma, I square it, plus, and you keep on doing it until the nth variable. Okay, so that's the process. And I hope that you recognize that this is a standard normal random variable. This is actually a standard normal random variable. How do we know? Because remember, when you have x as a normal random variable, so when x is a normal random variable and you want to convert x to z, the formula that you use is x minus mu over sigma. Okay, so again, we go back to this. X here is a normal random variable. So if you minus mu over sigma, it's standard deviation, then x here will be transformed into z. And what is z? Z is a standard normal random variable. So when standard normal random variable is squared, so that means z is squared, well, it means that it has a chi-square distribution. Remember, we go back to this discussion here related to this fact. When x is a standard normal random variable, and when you square it, the result here is going to have a chi-square distribution with 1 degree of freedom. Okay, so what we have next is okay, let's just leave it at that first. Now let's move on to the second part, minus. Okay, now notice that x bar minus mu squared can, this part here can be written as sigma squared over n, right? So n can be brought forward, so it will be sigma squared over n. So it is the same thing. Okay, and now I'm just going to focus on this part. Now I'm just going to explain what happens to this part. Okay, so here what we have is x bar minus mu squared over sigma sigma squared over n. So you can see that one way of writing it, so this is the same thing as x bar minus mu squared times with n over sigma squared, as is given by the original one here. Okay, so that's what's going on. Now what I can do next is I can again combine all the terms to be under one bracket, and you square it in the outside. So what happens is I can write down this in terms of x bar minus mu. So I can write down in terms of x bar minus mu over sigma over square root n, and you square it. Well, you can try and expand it, and you will see that if you expand these terms here, it becomes x bar minus mu, you square it, over sigma squared over, if you square this, you're just left with n. So you got sigma squared over n at the bottom. So that's another way of putting all together inside one bracket, and you just square it. I'm doing the same thing like this one, putting everything together inside one bracket and you square it. Okay, so I hope that you can recognize that this, the whole thing here, is a standard normal random variable. Okay, standard normal random variable. Remember when you have x bar, and then if you have, for example, well, this is the result. We know that x has normal distribution, therefore it tells you that x bar also will be a normal distribution. We have seen this in the sampling distribution of the sample mean. So if x, the original population, is normal, then x bar also is going to be normal with mean mu sigma squared over n. So if you want to change this normal random variable into a z, into a standard normal random variable, what you have to do is you have to take x bar minus the mean, its mean, and then you divide it with the standard deviation. The standard deviation is sigma over square root n. If you don't remember, or if you don't understand what I'm talking about, you really need to go back to the video related to the sampling distribution of the sample mean. Okay, therefore the whole thing here has become standard normal random variable, which is z. And you can see that z here has been squared, so z squared. So when you have a z squared, similar with the argument here, you have a standard normal random variable that has been squared, then this becomes a chi-square distribution. So it turns into a chi-square distribution. Okay? So let me just erase this because I need the space. So therefore, what I can do is maybe I can explain, can write down in terms of words. Okay, so I'm going to explain. So we know that based on what I have shown you just now, and based on my explanation, what we can say is that we recognize that this one here, so I'm going to call this A, this is going to be called B. So here A is actually a combination of standard normal random variable being squared, which is I can say that A is should I write down the result? Hang on, I'm just thinking how can I represent this. So here what we have is, okay, A is the process of having, let me just try and do this. Okay, so A is a process of having x1 minus mu over sigma, you square it, plus x2 minus mu over sigma, you square it, plus blah blah blah, xn minus mu over sigma, and you square it. And this is the same thing as having z1 squared. This is where z represents the standard normal random variable, plus z2 squared, plus blah blah blah, zn squared. And according to what you have seen before, therefore A has a chi-square distribution, because this is chi-square distribution, this is also chi-square, this is also chi-square distribution, and the degrees of freedom is 1 each. Therefore, A has a chi-square distribution with n degrees of freedom. So that is A. Where do these results come from? Remember, we have seen this similarly at this part here, where you have standard normal distribution, you square it, the result here is going to be as such. Okay, right. So that is A. Next, when we talk about B, well, B here is equal to, so B here, I'm just going to say B here is equal to, like I've shown you just now, x bar minus mu sigma over square root n, and you square it. And this is also a standard, a normal random variable, so we're going to call it z, and you square it. There's only one standard normal random variable, therefore B has a chi-square distribution with 1 degrees of freedom. Now, here is the process of subtraction. And here is what we're looking for. We're looking to show that this guy here has a chi-square distribution with n minus 1 degrees of freedom. Well, because this one is a chi-square distribution, this one is also a chi-square distribution, therefore, n minus 1 s squared over sigma squared must have a chi-square distribution as well. Okay, because both on the right hand side have a chi-square distribution, so therefore this guy here must have a chi-square distribution, where the degrees of freedom is supposed to be the summation of degrees of freedom that we have, but here because we have subtraction here, therefore the degrees of freedom is going to be n minus 1 is equal to n minus 1. So basically that is how you can roughly understand why the statement given in here is true. Okay, so this guy here has a chi-square distribution with n minus 1 degrees of freedom. Alright, I think that's all for now. Thank you very much for watching.